This lesson's about mass energy equivalence and the famous equation E is equal to mc squared. Here are the objectives. Let's start with an atomic mass unit and defining that. One atomic mass unit, which is given the symbol 1U, is defined as exactly 1/12 the mass of a neutral carbon-12 atom, including the electron, so it's a full atom. And one atomic mass unit is equal to 1.661 times 10 to the negative 27 kilograms. This gives us a more convenient unit for measuring very small masses. For example, the mass of a proton is 1.007276 atomic mass units, and the mass of a neutron is slightly larger at 1.008665 atomic mass units. Now, you might already be noticing the fact that a carbon-12 atom has 6 of each of these, plus electrons, and yet its mass is less than the sum of 6 times this plus 6 times this. From the definition we've given here, the mass of a neutral carbon-12 atom is exactly 12 atomic mass units. So what's going on? How can the whole be less than the sum of the masses of the parts? Well, to understand that, we need to go a little bit further, and we'll do that over this lesson and the next. Let's start with understanding what Einstein's famous equation E is equal to mc squared is telling us. So E is equal to mc squared. E stands for energy, m is mass, and c is the speed of light. And the speed of light is equal to 3 times 10 to the 8 meters per second. What this is telling us is that mass and energy are two sides of the same coin, just related by a conversion factor, c squared. Mass and energy are actually equivalent, and they are interchangeable. In other words, if you were to increase the energy of something, you would increase its mass. You can rearrange this equation to show that mass is equal to energy divided by c squared. Again, c squared is just this number, 3 times 10 to the 8 meters per second, squared. So if you were to increase the energy of something, you would increase its mass. The mass of something is actually a reflection of the energy that it has. So if you were to wind a clock, you'd be increasing the potential energy and the kinetic energy of the parts of the clock. That would increase the mass of the clock. If you were to heat water, that would increase the thermal energy of the water, and that would increase its mass as well. So why don't we notice these things on an everyday basis? Well, it's because this number c squared is so humongous. Even a substantial change in energy when divided by this number 3 times 10 to the 8 squared is going to give you a relatively small change in mass. So winding a clock, heating water, they actually do increase the mass of the clock, increase the mass of the water. But because c squared is so big, that change in energy results in a very small increase in mass. Looking at this the other way, if we could convert mass into energy, then a tiny mass converted into energy would give us lots and lots of energy. And that's the principle behind nuclear power plants. Tiny amounts of mass are disappearing in the fission reactions in those power plants, and that's liberating lots and lots of energy. So it doesn't really make sense anymore to talk about the law of conservation of mass or the law of conservation of energy on their own anymore. Now we have to talk about the law of conservation of mass energy. So what we'll see with nuclear reactions is that mass is actually not the same on both sides, and neither is energy. But if you total up all the mass and all the energy on both sides, it's equivalent. So we're now going to replace the law of conservation of mass and the law of conservation of energy with this one law, conservation of mass energy. Einstein's insight with this equation, E is equal to mc squared, is that things have energy by virtue of having mass. Mass itself is like a kind of storehouse of energy, and we can get that energy out in reactions where mass disappears. So we've talked about this equation, we've talked about atomic mass units. Now we can ask, how much energy is there in one atomic mass unit? In other words, if one atomic mass unit were to disappear, how much energy would that release? So we need to use SI units, so we're going to use kilograms instead of atomic mass units, and we'll start from our equation E is equal to mc squared and plug in one atomic mass unit worth of mass, but in kilograms. Now we need to multiply that by c squared. We said that c is 3 times 10 to the 8 meters per second, and that's all squared. And when we multiply that out, kilograms by meters per second all squared, we're going to get joules. So we get 1.49 times 10 to the negative 10 joules. Now that's a very small number, so let's convert that to electron volts. remember that to do that, we need to multiply by a conversion factor, and that conversion factor is that 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules. Remember, an electron volt is the energy that is gained by 1 electron, 1.6 times 10 to the negative 19 coulombs, as it passes through a potential of 1 volt. So this is our conversion factor, and when we multiply that out, we get approximately 9.3 times 10 to the 8 electron volts. Now, this is a very big power of 10, so we can convert that to mega electron volts. A mega electron volt, that's a million electron volts, or 10 to the 6 electron volts. So this gives us approximately 930 mega electron volts. In other words, when one atomic mass unit is converted into energy, we get out 930 mega electron volts of energy. Now, we're actually going to use a slightly different number than that. You'll see slightly greater precision, where one atomic mass unit gives us 931.5 mega electron volts. Now, this is a unit of energy, and an atomic mass unit is a unit of mass. So we don't have the same units on either side, or the same kinds of units on either side. So this isn't really an equation, but we could write it as an equation by writing a different kind of mass unit over here. So we're going to use this funny looking unit, which is a mega electron volt divided by c squared. So this now is actually a unit of mass. And where does that come from? Well, if you go back to your equation E is equal to mc squared, and you rearrange it for mass is equal to energy divided by c squared, we're just including this in our unit. So what 931.5 mega electron volts per c squared tells us is it's the amount of mass that, if it were converted into energy, would liberate 931.5 mega electron volts. The divided by c squared there is just a shorthand to make it into a unit of mass. So don't be put off by that. And we're going to use this relationship that one atomic mass unit gives us 931.5 mega electron volts when we look at the energy that's released in nuclear reactions. So that's an introduction to mass energy equivalence and the famous equation E is equal to mc squared.